Hi, I Aziz welcome you to CoedMaster, and in this video I am going to talk about this problem. So let's get started. Let's see this problem. We are given a number and we have to find position of only set bit in a given number. And if a number is equal to 0 or if number is having more than one set bits, then we simply have to return -1. Okay? So to understand this problem really well, let's see few examples. So in first example, the number is 2. The binary representation of number 2 is 0010, and you can see that it has exactly one set bit and the position of set bit is 2. This is first position and this is second position. Okay? Let's see next example. Here the number is 5. The binary representation of this number is 1001. And you can clearly see that this number is having more than one set bit. That's why we are returning -1. In next example, the number is 4. The binary representation of number 4 is 0100. It also has only one set bit and the position of that set bit is 3. 1, 2 and 3. Okay, I hope now the problem is clear to you. So let's pause this video and think about an algorithm to solve this problem. So I hope by now you would have written at least basic program to solve this problem. So let's see the brute force approach to solve this problem. The idea is pretty simple. We first initialize two variables, count and position. Count variable is going to count number of set bits and position variable is used to hold the position of set bit. Then we simply traverse from least significant bit to most significant bit, and in each iteration we check if bit is set or not. If we found that bit is set, then we store the value of that iteration in position variable to know the position of that bit, and along with it we simply increment the count by 1 to get the number of bits in a number. And after traversing all the bits, in the last we check if count is equal to 1 or not. If count is equal to 1, then we return position plus 1. Else we simply return -1. It means if we get count equal to more than 1, it means there are 2 bits present in the number. So that in that case we have to return -1. And why we are returning position plus 1? Because binary numbers are based on 0 index and the position is based on 1 index. Means the first number is at the first position, but in binary representation the bit is at the 0th position. Okay, I hope you got it. Let's see the implementation of this brute force approach. In this approach we have a function. This function is taking n as input and we are initializing two variables. One is for position and one is for count, and then we are simply running a loop 32 times for each bit in a number, because integers are represented by 32 bits, and in each iteration we are checking if bit is set or not. So we check if first bit is set or not, then we move on to second bit, then we move on to third bit, and like so on and so forth. Here one left shift I means we are shifting bit towards most significant bit. In first iteration the bit is set to 0th position. In next iteration bit is set to first position. In next iteration bit is set to second position, and we are doing bitwise and with number. If we get number that is not equal to 0, it means the bit is set, and in that case we increment count by 1 to calculate the number of bits, and we store the position as I, because at ith position we found the set bit. And in the last, if we get count is equal to 1, then we are returning position plus 1. Else we are returning -1. So let's dry run this code and see how it works. So in case of n is equal to 4, the binary representation of number 4 is 0100. In first iteration I is equal to 0, and we can see that there is no set bit in 0th position. So we move on to next iteration. In next iteration I becomes 1, and we again see that on first position also there is no set bits. We move to next iteration. In this iteration I becomes 2, and we can clearly see that on second position we have a set bit. So in this case, we store the value of I in P to get the position and increment count by 1. So the value of count becomes 1. In next iteration, I becomes 3. And in third position, in third index, you can see that there is no set bit. So our loop gets completed and we get output as 3. Why? The value of position is 2 and 2 plus 1 is equal to 3. And you can see that at third position, we have one set bit in number 4. Let's see the another example. In case of n equal to 5, the binary representation of number 5 is 0, 1, 0, 1. Okay. When we run this program, our loop begins. In first iteration, the I is equal to 1. We found that bit is set. So we simply set the position as 0 and count to 1. In next iteration, I becomes 1. And we check that there is no set bit at position 1. Then in next iteration, I becomes 2. At second index, we have one set bit. So we store the value of I to P and we increment count by 1. So now the value of P is equal to 2 and count is also equal to 2. In next iteration, our I becomes 3. And in third position, we can simply see that there is no set bit. So in next iteration, we come out of this loop. And -1 gets printed on the screen. Why? Because this time the value of count variable is 2. It means there are 2 set bits in this number. And when we hit this condition, we simply returns -1. Okay, clear. Now talking about the time complexity of this function, it might be possible that in worst case, you get number like this, 1, 1, 1, 1. Okay. If you get this number, then you have to traverse all the bits, obviously, to check the set bit. So if you take a log of this number, and actually this number is 15, and if you take log of this number, you can simply find the number of bits required to represent this number. So log of 15 is 3 and 3 plus 1 is equal to 4. So there are 4 bits required to represent number 15. And we are also traversing all the bits. So that's why in worst case, the time complexity of this function is going to be big of log of n. Okay. And space complexity is theta of 1 because we are not using any auxiliary space or extra space. We are simply using all the variables. I guess only 2 variables we are using. That's why, no, sorry, not 2. We are using variables like n, position, count and I. So there are 4 to 5 variables we are using. So that's why the space complexity is constant, theta of 1. By looking at this solution, I am thinking that we can optimize this code better. We can do something better because we are doing here a lot of work. Okay, so let's see how to optimize this code and find solution of this problem in more efficient way. So let's see how we can solve this problem more efficiently. And to get the idea of how to solve this problem efficiently, we need to know some facts. And the fact is, we can directly find the position of one bit if any number has only one bit. And how is this possible? Let me show you. If you consider binary representation of any number, you see that all the bits here representing power of 2. This bit is representing power of 2 as 2 to the power 0. This bit is representing 2 to the power 1. This bit is representing 2 to the power 2 and this bit is representing 2 to the power 3. And if the number has only one bit set, then obviously that number is going to be a power of 2, right? In case of 4, only one bit is set and it is a power of 2. 4 is a power of 2, right? So to get the position of this bit, what we have to do, we simply have to take log of 4 and add 1 to it. And when we do this, we get the position right away. So we do not need to do anything if we know that a number has exactly one bit, one set bit. This way we can directly find the position of that bit. So this is the one fact. So this is the fact we need to know. Okay, moving on. But what about the number that is not a power of 2 or 0? So in these cases, we simply have to explicitly handle condition for 0. And second, for number that have more than 1 bits, we simply have to explicitly check if number has more than 1 bit or not. And how to check if a number has more set bits or not? Simply we can use Brian-Kernigham's algorithm here also. So let's understand how we do it. So in case we have 2 and 2 is a power of 2, right? If we apply Brian-Kernigham's algorithm, it means we have to do bitwise AND with 2 minus 1, that is 1. We get 0, right? It means there is only one bit set, and that is unset by Brian-Kernigham's algorithm. If this number would have more than 2 bits, then we will get number other than 0. It's simple, straightforward. So here we can use Brian-Kernigham's algorithm to find that a number has more than 1 bit or not. So this is how we are handling explicitly for 0, and we are handling explicitly for numbers that has more than 1 bit. So let's see the implementation of this efficient approach. So we have a function. This function is taking n as input, and in first line we are handling both the conditions. First condition is if n is equal to 0, then return 1, and this is the second condition where we are applying Brian-Kernigham's algorithm. After applying Brian-Kernigham's algorithm, if a number has more than 1 bit, then it is definitely not equal to 0. So in this case we simply returning -1. If number is not 0 and number is not having more than 1 bit, then we are simply calculating the log of that number and returning position +1. Okay, so in case of n is equal to 2, the binary representation of number is 0, 0, 1, 0. Okay, this number is not equal to 0, and even if we apply Brian-Kernigham's algorithm, we get 0. So we are never get into this if statement. So after if statement, we are calculating log of this number. We get 1 and we are adding 1 to it. So we are getting position as 2. And we can see that at second position, the bit is set. In case of 5, the binary representation of 5 is 0, 1, 0, 1. When we run this code, our n is not equal to 0, but when we apply Brian-Kernigham's algorithm, we get a number that is not equal to 0. Because after unsetting the first bit, we still get a number, okay, and that number would be 4. So that's why the output of this input is -1. Okay, great. Now talking about the time complexity of this function, you can see clearly that we are not performing anything other than constant operation, because all these operations are constant operation. That's why the time complexity is θ1, and space complexity is also θ1, and space complexity is also θ1, as we are not using any auxiliary space to solve this problem. So far so clear. So before we end this video, let's have a quick recap of what we have learned so far. So we are given a problem, and our task is to find the position of set bit in that number. We saw the brute force approach to solve this problem, and the time complexity came out to be big of log of n. And after brute force approach, we saw the efficient approach to solve this problem, and the time complexity came out to be θ of 1. That is much better than big of log of n. So I hope now you have good understanding of how to find position of set bit in any given number. So this is it for this video. Thanks for watching. See you in the next video.